The mean value theorem is relatively important, not because we use it a lot, but the consequences of the mean value theorem, which we'll get to tomorrow, namely increasing and decreasing intervals on which a function increases and decreases, are really important. So that's why it comes up. So you need to be able to find the value guaranteed by the mean value theorem. You'll know what that means. If you're in my class, you've done the exploration, you know visually what that means. And then the other part, whenever you're going to use the mean value theorem, you need to write the prerequisites for the mean value theorem before actually using it. Much like problems with continuity, hey, find this value that makes f continuous, you need to start out with that kind of formal version. So, in terms of definition, the way I'm going to say the mean value theorem, if a function f, could be g, h, whatever, if a function is continuous on a closed interval, a to b, and differentiable on that same open interval a to b, then there exists at least one x value, x equals c, on the open interval a to b, such that, well, let's figure out what this means. So, continuity shouldn't be a problem. So we need a function to be continuous on a closed interval a to b. And that same function has to be differentiable on that same open interval a to b. And you'll notice the picture I have here. Well, at b, this graph has a discontinuity. But this graph is differentiable at all x values in between those endpoints. And yeah, it says 0 and 3 on the graph, but just a and b are stand-ins for whatever the x coordinates are. Okay, so we need a graph that's continuous on a closed interval and differentiable on that same open interval. Then something exists, and the thing that exists, and we'll see it here in a second, well, what you see drawn is a secant line connecting the endpoints. And what exists is a tangent line parallel to that secant line. So the mean value theorem guarantees that an instantaneous rate of change is equal to an average rate of change. Slope of a tangent line equal to slope of a secant line. And that's the way we write that symbolically. So what's guaranteed is f prime of c, and that's just slope of the tangent line. And c is just someplace. And notice that c has to be on the open. It's somewhere between the endpoints. And the slope of the tangent line is equal to the slope of the secant line connecting the endpoints. So that's kind of all there is. Now, you might... Oh, shoot. Sorry, I thought something else was next. So in other words, the mean value theorem establishes when an average rate of change is equal to an instantaneous rate of change. Usually with the theorem problems, you're not told, hey, use the mean value theorem. You'll have to kind of figure it out. So a common mean value theorem problem, it'll have some phrase like, hey, must the particle have this particular velocity? Or maybe you're given a table of x and y coordinates, and I'll show you one of those at the end. I think it's from 2022. A table of x and y coordinates, and hey, does the derivative ever equal some number? Which you really can't do from an average rate of change, and you're supposed to think, oh yeah, mean value theorem. Okay, so something else that might come up, you might see words, and that's Rolle's theorem. Now, Rolle's theorem is very similar to the mean value theorem. It gets its own name because it was proven first. It was easier to prove mathematically. So anyways, notice almost sounds the same. If a function f is continuous on the closed interval a to b and differentiable on the same open interval a to b, and then here's how Rolle's theorem is different. It says f of b is equal to f of a. And so that's our major difference. And what that means is that the y values of the endpoints are the same. Then there exists at least one x value. So notice again we have a secant line connecting those endpoints. But if f of b is equal to f of a, right? That's this y value, which in this graph is 0. If they're equal, then we're guaranteed not just a tangent line equal, oh shoot, I have this backwards. Oh, no, I don't. Okay, sorry. Not just a tangent line equal to the slope of the secant line, but if those y values of the endpoints are the same, like let's say that secant line was up here, and instead of this one, you know, A and B are somewhere else, then we're always going to get a horizontal tangent line. My recommendation is just know that Rolle's theorem is a special case of the mean value theorem, and you can always use the mean value theorem. Just if that phrase comes up, you'll need to know it. Okay, so how do we actually do this? We'll practice, I don't know, in the abstract, just, hey, how does this work? So we need to find the value guaranteed by the mean value theorem for g of x, which is 4 minus x squared on negative 2 to 1. And the first thing you have to figure out is, hey, can I use the mean value theorem? Well, let's picture the situation. So 4 minus x squared, pretty easy parabola to sketch. And, you know, a parabola is a polynomial. Polynomials are continuous and differentiable everywhere. This will work out. And then let's see. So on negative 2 to 1, we're going to be finding the slope of that secant line, whatever that is. And is there going to be a tangent line parallel to that secant line? There sure is somewhere. I don't know, negative, in between negative 2 and 0. We'll figure out exactly where that is in a moment. So before you start, you have to say that you can use the mean value theorem. G of x is continuous on, we don't write the words closed interval, we just write the notation. Closed interval, negative 2 to 1, and is continuous on the open interval, negative 2 to 1. So the mean value theorem applies. I don't know, a quick word. So if you know, g of x is continuous and differentiable everywhere, but we want to practice that structure of, hey, continuous on the closed interval. I wasn't even paying attention. Differentiable on the same open interval. If you're always relying on polynomials and kind of this shorthand when things get complicated, you may not know. Anyways, so what are we looking for? We're looking for the instantaneous rate of change equal to the average rate of change. And my recommendation is start with the end in mind. Don't calculate everything separately. Just, hey, we're looking for where this slope of a tangent line is equal to the slope of the secant line. And so I've made these kind of color-coded to match. So g prime of c is the derivative of g at this point c that we're looking for. We don't want to use x because x is a variable. It stands for all possible inputs. Anyways, and then on the right-hand side in pink or whatever you want to call that is g of 1 minus g of negative 2 over 1 minus negative 2, right? Slope of the secant line. So now all we have to do is simplify, 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 and everything's going to be nice and organized, and we don't really have to explain our work. So g prime of c, that's a pretty easy derivative. Derivative of 4 is 0. Derivative of negative x squared is negative 2x, and you put in c and get negative 2c. I'm going to write out the work for g of 1, 4 minus 1 squared, and then minus 4 minus negative 2 squared. And hopefully you can see this big chunk is going to be 0. And then notice we just have to keep simplifying. Still negative 2c on the left. And on the right, 3 minus 0 over 3. And you can see we're just going to get c is equal to 1 over negative 2. So that's what we found out here. Not quite enough room. Negative 1/2 does seem about right. And notice because we started with this structure that the slope of the tangent line is equal to the slope of the secant line, we can do a lot less explaining at the end. We don't have to put things together. We don't have to remember. Everything's already organized. So what I'm certain is that past students, and so future students, think that their job is something other than it is. You have to do all of the work I just showed you and all of the explanation. And so when I say start your calculations with the final result in mind, that's what I'm saying right here. Right here, start with the final result in mind. We want to know where the derivative is equal to the secant slope or something like that. Let me say that another way. This warning is like, a lot of people think that if I get -1/2, no matter how I get it, then I'm correct. And well, in an ideal world, I suppose that would be true, but your job is to show what you know. And in this case, what College Board, what I'll be looking for is, do you know how to use the mean value theorem? Not can you find a number? Because, I don't know, you could look up that number or something. We're kind of testing knowledge here. So what do you need? Well, if you're going to do the mean value theorem, you need to say why you're allowed to. You need to have average rate of change equal to instantaneous rate of change. And so I suppose if you want to do the minimum amount of work, you definitely need this line. You don't need a graph, but if you don't know the shape, you're kind of in trouble. We do need to show the derivative g prime of c somewhere, and the notation that we're doing the derivative. And so you probably need a line like this. You could skip some of the work and you definitely need a result. So you could do slightly less, but I don't think that's a great idea. Okay, so let's try that again. So find the value guaranteed by the mean value theorem for the function h of x, x cubed minus 9x, on the closed interval -3 to 3. And again, I've given you a polynomial so we can worry about the mechanics of how do we do this, not are we allowed to do that. So x cubed minus 9x has zeros at 0, -3, and 3. Hopefully you can easily factor that in your head, which means, I guess this is a Rolle's theorem case, but I'm not going to use that. We can just use mean value theorem always. And also, hopefully, we're going to get two results, right? There are two places where x cubed minus 9x has horizontal tangents between -3 and 3. So what do we start off with? H of x is a polynomial, so h is continuous on the closed interval -3 to 3, and differentiable on that same open interval -3 to 3, so the mean value theorem applies. And we're just going to write down what we did visually, that the slope of the secant line, h of 3 minus h of -3 over 3 minus -3, is going to be equal to the slope of the tangent line, h prime of c. And I guess we're going to get two c's, c1 and c2 or something like that. I don't know if that's going to matter how we write that, so I'm not worried about it now. Okay, so h prime of, I think we're doing the right-hand side first in this one. So h of 3, that's just 3 cubed minus 9 times 3. Hopefully you'll notice, that's 0. And -3 cubed is -27, plus another 27 is another 0. So indeed, we do get a slope of 0 for that secant. Anyways, h prime of c, 3 times c squared minus 9. And then we'll simplify the right-hand side a bit. And hopefully you can see, we just add 9, divide by 3, c squared is equal to 3, and we indeed get positive square root of 3 and negative square root of 3. With symmetry and the fact that x cubed minus 9x is an odd function, that all makes sense. All right, one last example, which we're not really going to do. I forget. I think it's 2022, maybe 23. So the first problem is a calculator problem, gives you a table of values. And I've crossed off part A because I don't want to think about it. A customer at a gas station is pumping gasoline into a tank. The rate of flow of gasoline is modeled by a differentiable function f, where f of t is measured in gallons per second, and t is measured in seconds since pumping began. Selected values of f of t are given in the table. Okay, so there we go. Part B here, this is actually mean value theorem. Notice it doesn't say that, but you kind of have to figure it out. Must there exist a value of c somewhere on 60 to 120 such that f prime of c is equal to 0. Justify your answer. So what you're supposed to figure out is, okay, I'm given f of t and I'm asked about f prime of t. What relates average rate of change to instantaneous rate of change? Mean value theorem. Another way to say that is, you're given a table of values. There's no way you're figuring out what f, the function, is. Like if f is e to the x plus cosine of something. Right, you can't do that. So it's got to be a theorem-y thing. And there's another hint here where it says, must there exist? We're not going to answer it as yes and no, but essentially those are the two choices. Must there exist? Yes, there must exist, or maybe no, there must not exist. Anyway, so that's what mean value theorem would look like. Maybe I will do it. So the first thing you have to figure out is, does the mean value theorem apply? And the answer is, of course, yes, but you kind of have to say a little bit more. So the first thing we start off with is f is differentiable. That was given. And then you have to make so f is continuous. So you're given basically a point for that logical step of knowing that the fact that a function has a derivative means that function is continuous. So the mean value theorem applies. And you could write a little bit more, but that's probably good enough for College Board. And what does that mean? Well, we said f prime of c is going to be equal to, and well, I guess I thought of something before I wrote this. What did I think? Well, when I box this back up here, what we notice is f of 60 is 0.1 and f of 120 is 0.1. So in my head, I've already thought that f of 60 minus f of 120, I should do those in the other order. F of 120 minus f of 60 over 120 minus 60 is 0. And that should be equal to f prime of c, because that's just average rate of change equals instantaneous rate of change. And there's a little bit more, but hopefully you get the idea.